Hello everyone, this is Team 6T and our presentation today is DPGMVAE, Deep Infinite Mixture Latent Variable Model. Our presentation will be divided into 4 parts. First, we will introduce the background and the problem. Then we will introduce the baseline model and our DPGMVAE model. Extensive experiments are shown afterwards. Finally, we will come to the conclusion. Typical unsupervised clustering models are machine learning models which are hard to capture hidden structure. To solve this problem, deep learning methods are introduced. Since VAE has latent space and this latent space can be used to perform unsupervised clusterings, VAE series models like GMVAE are extensively studied in unsupervised clusterings. As for the current problem, however, using GMVAE models, we need to specify the dimension of latent space. We want to extend the GMVAE model by introducing DPGMM to extend the latent space with infinite mixture model. Our novelty is to use the non-parametric mixture models on the latent space of GMVAEs to do unsupervised clustering task.
In this project, we start with a VAE extension for unsupervised learning, GMVAE, as our baseline model. The basic idea is to replace the unimodal assumption with Gaussian mixtures. Here we can see its graphical model, where a categorical variable y represents the class of the data to be generated, and z is the latent variable conditional on y that follows a Gaussian distribution. When doing the inference, we will first learn y based on input x, and then the distribution of z based on x and y. Similar to VAE, GMVAE is learned by maximize the evidence lower bound, but this time it contains 3 loss terms: a reconstruction loss to compare the similarity of original data and generated data, a Gaussian loss forcing the latent distribution to be close to prior distribution, and a categorical loss for learning y from a combo softmax. Here is the detailed model structure. The problem is we have to specify the number of cluster k in GMVAE, which is not always known in real-world scenario. The racially processed Gaussian mixture models provide a tool to deal with this problem. So we first try to implement DPGMM on the latent space of GMVAE. We found that even with small k specified in GMVAE, DPGMM is capable of finding a larger number of clusters and achieve better clustering performance. Based on this knowledge, we went one step further and proposed a DPGMVAE model, where we directly replace the prior distribution with the ones derived from DPGMM. We do this replacement alternately, and this way, better clusterings could be learned in the latent space.
As for our data, we have 2 datasets for implementing and verifying this model. The first dataset is the MINIST dataset, which is a very famous deep learning dataset with handwritten digits. And the second dataset is about the fashion MINIST dataset, which is a grayscale dataset for 10 categories of clothes.
This experiment shows how data is clustered in latent space learned by GMVAE during training on MINIST. Different colors indicate different ground truth classes, and the clustering accuracy at the corresponding epoch is reported in the bracket. It is clear to say that latent representation become more and more suitable for clustering during training, which can also be proved by the increasing clustering accuracy. In this experiment, we specify different k, which is the number of components in GMVAE, as 2, 3, 5, and 10. Then with each k, first, we compare the predicted label with ground truth within the latent space of GMVAE. Then, we use the GMM to cluster latent feature of GMVAE and calculate the accuracy. In the end, we use DPGMM to cluster latent feature of GMVAE. As we can see, in either MINIST or fashion MINIST dataset, we can see either significant or slight increase in accuracy in each case. It tells us that DPGMM learns a better distribution than GMVAE itself. We can't help thinking if we use the distribution obtained from the DPGMM to replace the ones in GMVAE, we can get even better results. And this is the whole idea of our project. Let's see our result. The first 3 models are our baseline, as I explained earlier. The fourth one is what we proposed. We can see in our proposed DPGMVAE, we can get 91% accuracy in MINIST dataset, which is a relatively great improvement over the original model. In the end, here comes to our conclusion. Simply speaking, we can get improved performance on GMVAE by using DPGMM. And in the future, we might explore using other non-parametric mixture models on the latent space of the other SOTA models. Thank you.